Hello and welcome to the AIM webinar series. AIM is a global industry alliance which represents the interest of everyone using barcoding, RFID, and related data capture technologies, including manufacturers, software vendors, integrators, governments, and end users. AIM membership is about supporting standards, community, advocacy, and knowledge. Specifically, you will receive early access to industry technical research and information. AIM is an investment in your future. Before we get started, I have a few housekeeping notes to go over. First, as you may have noticed, all participants are muted throughout the presentation. We will have several points during the webinar for Q&A sessions. If you would like to ask questions, please send those at any time to me by clicking the chat option located on the bottom tab on the webinar screen. Select AIM Member Services and submit your questions. This webinar will also be recorded and you will be notified when the recording is available. Today we have several subject matter experts discussing the AIM DotCode International Symbology Specification 4.0 revision, how the revisions came to be, and share what the revision means to the industry beyond packaging and distribution. Our speakers today are George Wright, who is the DotCode Project Editor and Vice President of Product Identification Processing Systems, Terry Burton, who has been a key DotCode contributor and Director of Terry Burton Consulting, and Scott Gray, Solutions Architect for GS1 Global. Welcome, gentlemen.
Hi, Mike.
Hi.
Thank you, Mike. Nice to be here.
Thanks, Mike.
To start, we will have Scott Gray discuss fighting illicit trade and how DotCode factors into this. Scott, take it away.
Thank you, Michael. So the fight against illicit trade is an effort focused in Europe, at least at this time, and within the sector for tobacco supply chain. It's based on a World Health Organization treaty, and so we can expect that the fight will expand outside the European borders, but they've taken a very comprehensive approach to it. It's a serious problem with about an estimated 10 billion euros per year in illicit trade of tobacco. And so GS1 members are active in this space. We've developed, or they have developed the standards to fight illicit trade. And the key is to utilize as best we can and everywhere we can GS1 standards that are used in the supply chain to help in this fight, so that we reduce duplication and promote interoperability between supply chain solutions and regulatory solutions. So again, this is in support of the World Health Organization, the European Commission, and EU member states. And at present, that's 27 member states of the European Union. We're trying to support, again, our members who have already invested in infrastructure and processes and data based on GS1 standards. So to the degree that we can leverage that in order to meet the regulation, then that's to their benefit and to the regulatory body's benefit, in that it provides scale, interoperability, and speed. Of course, we're also a neutral partner, so we're trying to provide this help and in a way that enables solution providers and the secondary repository provider of the Commission. So the GS1 approach is maybe different than a lot of different organizations who may focus on one area or another. We begin, yes, as an ISO IEC issuing agency, and with the identification toolbox that we have, which fortunately supports all of the identifiers necessary or required by this law. We had to enhance our toolbox for the data carrier offering in order to accommodate a new barcode, DotCode, that has been specified within the law. We'll talk more about that later. But otherwise, we already had all of the data carriers in our suite, so we're fully supported there. Of course, our identifiers work with our data carriers per ISO standards, ISO IEC standards. And we also provided a full suite of master data, traceability data, and transaction data standards that can be used with the previous two. We had to go further than our typical offering to provide some special adaptations of a serialization scheme, which we'll talk about in a moment. But all of that wrapped together to provide interoperable market surveillance for the European Union while leveraging the currently installed set of tools that our members have been invested in for many decades. So if we look at the summary of how the regulation impacts the tobacco supply chain, the first is that it starts with the manufacturer at the point of production, and it traces or tracks this unit pack all the way to the back end of a store. So not to the point of sale, but to the receiving at the store where it will be sold to the consumer. That could also find its way to a vending machine, because a vending machine represents the retail point of sale. So if it's a distributor is stocking a vending machine, it has to be tracked to that point. Unit packs have to provide a small business message required by the WHO, and they have to do that when scanned in offline mode. Now, that message is a bit large to print at high speeds, and so with the unit packs only accommodating 50 characters for high-speed barcode printing, an algorithm and flat file design was selected, and we'll talk about that more in a moment. Some different things about this is that the G10 serial numbers, the global trade item number serial number, must be allocated by a third party rather than the manufacturer. Fortunately, for packaging above the unit packs and for logistics units, the current identifiers of GS1 are accommodated. Now, the barcodes that are used at the unit pack level include, again, the new barcode GS1 DotCode. DotCode is the symbol specification, and when we say GS1 DotCode, that means that the DotCode carries an ISO IEC 15424 symbology identifier that tells that's transmitted with the message to say what you're about to see from this barcode is defined by the rules and standards of GS1. So that's where the nomenclature GS1 DotCode pertains. So for unit packs, it's GS1 data matrix, QR code, or DotCode. And for higher levels of packaging and logistics units, data matrix, QR code, but also the linear GS1 128. As I said before, the identification covers other areas besides products. For instance, the production machines where tobacco product is made, or the facility or the economic operator. And for that, GLN, the global location number for parties, or the global location number for locations can be used, along with the asset identifier for the machine. In the data sharing level, we have three messages: orders, invoices, and payments from the electronic data interchange side, and of course the full EPCIS suite for reporting primary event data. So I spoke about the unit pack, and the solution was a bit different than what we typically see. So in the center of this slide at the top, in the light blue box, you'll see a typical message for what needs to be communicated to a customs official. So when they scan the barcode, even if they're in offline mode, they need to be able to retrieve a lot of information about what that unit pack of tobacco, where it was made, what machine it was made upon, some basic product description, and of course the identifier itself. Now, to arrive at that message, it means that the scanner itself needs to support what's called a flat file design. So a small database that then relates to the algorithm and the serial number The algorithm and the serial number then allows for the index or lookup of different information in the database to produce that small message. A GS1, you can see an example of the GS1 algorithm or serial number in the orange box to the right at the top, where you see in parentheses 235, that's the application identifier for a third-party controlled serial number. And we'll talk a little bit more about that identifier in a moment. Timestamp is optional, but again, it does require that imaging-based scanners capable of scanning DotCode must be deployed wherever the unit packs are scanned. So in order to support the implementation, you first start with the data carriers. You need to be able to support GS1 data matrix, GS1 QR code, and GS1 DotCode wherever the unit packs are sold or scanned. This also includes, barcode design, printing, verification, processing. Supporting data matrix, QR code, and 128, where the higher level product packaging like cartons, master cases, and logistics units are scanned. And of course, support the new type of serial number and the processing needed to produce a G10-based unit pack unique identifier, or UPUI. So I want to talk about the actual construct of this third-party serialized extension of G10. So if you see the TPX, that's the acronym we use for this, third-party extension. And in this example, you see the specifications at the same level as you'll see from the commission and the secondary repository. The symbology identifier is required. In this case, we're using DotCode as our example. For DotCode, you see a back bracket J, which has to be transmitted from a decode to the processing software. And if it's a GS1 DotCode, following the back bracket J, you see the numeral 1. So when a system sees that, it says, I'm about to interpret what's in the barcode based on GS1 rules, which then means the scanner system is looking for a data qualifier. Now, in GS1's case, a data qualifier is an application identifier, or where you see in the column AI. So AI 235 tells the system that it's seeing a third-party serialized extension of G10. Most of the time when you see examples of serialized G10, you see the G10 first, followed by the serial number. In this case, it's mandatory that the serial number comes first because of the need for the starting characters of the total identifier to become what's called a unique identifier code by the commission. I won't go into great detail about that, but we do have more information. We can share links to some of that information with AIM if you should require it. The TPX is a variable length code, so it's not fixed length. Therefore, there must be a group separator to say where that field ends. And then you see the AI for the global trade item number. And if it's encoded in the barcode, the AI for the timestamp, which is only encoded to the precision of the hour. So as far as our data capture rules, you ensure the barcode design printer software produces the correct start pattern that's specified in each barcode specification. So for instance, for DotCode, you will find the specification for a GS1 DotCode means the function one character is not present in the first position. And I think the Terry and George will talk about that later in the presentation at a more technical level, so I'll just move past it for now. But each barcode specification tells how to communicate or transmit a symbology identifier which signals GS1 data. Ensuring the sequence of the application identifiers is always the third-party serialized extension first, then the global trade item number, then the timestamp, and the timestamp is only to the hourly precision, but to the hourly precision. Ensure there's a group separator placed between the TPX and G10 elements. Next. Ensure the symbology identifier, AIs, and group separator is removed when the TPX, G10, and timestamp are concatenated in that sequence to form the unique identifier, the unit pack identifier. So the data qualifiers in front of those data elements are not a part of the identifier themselves. They simply help the processing software understand what is being processed. Never encode the third-party serial number with a brand owner determined serial number. So you never have two serial numbers encoded in the same barcode that conflict. And for present application, we use this third-party serialized identifier only for the European fight against illicit trade. The default position of GS1 is always brand owner determined identifiers. That's the default practice. This is a very special case because we're fighting illicit trade where the commission decided that a third-party serial number is required. Also, for the present, GS1 DotCode has been approved, but only for this application. If its application were to go further, it would be approved through our standards process for a new application standard. But at this time, it's only for this fight against illicit trade. And with that, I will give the floor back to you, Michael, and happy to answer any questions or address any comments.
All right, thank you, Scott, for your time today, and thank you for the information you've provided. I do have a few questions I will go over now, but if you do have questions, we still have time. You can just chat those over to me. One of the questions I did receive is about the unit pack solution, and they were just wondering how exactly does that work offline?
So each of the manufacturers, when they apply or as they apply for the unique identifiers, they are required to provide a certain set of master data about those products. And then that is placed into a registry. The national registry in each country contains information about the economic operator. So for instance, the manufacturer or importer. It contains information about their production facilities, their machines that they produce with, cigarettes, and in this case, it's pouches of tobacco and cigarettes at this stage. It also ask them, as they request identifiers, to provide some transactional information. In other words, how many identifiers are they requiring for a production run? What facilities and machines will be used for that production run? Where that production is intended to be sold? And what is the route of transport to that, or at least the first country in the route of transport for that shipment to that country of export. Now, all of that information is gathered, and some of that information is required to be communicated to a customs official. So the customs official's device, eventually what they're still working on I would call it the consolidated decode solution. But essentially, if you take the different algorithms, so for instance, if I have 10 machines and I use one numeric character, I can identify those 10 machines. Obviously, this is an extraordinarily complex algorithm. and it has to provide a lot of different lookups. But the flat file that comes from the national registry, so there's an extract of the national registry data to create a small flat file of the information needed to produce that business message. When the barcode is, and that small amount of flat file data has to be resident on the offline scanning device. When that device sees a barcode and scans it, by looking at the symbology identifier, then using the rules that are used for identification at the ISO IEC level, it can then say, okay, I see a GS1 barcode, I see a TPX. We, GS1, working with the countries that we're working with, can communicate the algorithm processing to the decoder. That I see this. If I decode per the algorithm, then that means I need to look up this piece of the flat file and that piece of the flat file and compile this message. So I think, I guess that's a high-level explanation. We could probably honestly do 30 minutes just on that answer, but I hope that gives you at least a high-level understanding of how it works.
I think it does. Thank you. Another question we received, is all this taking into account blockchain?
The use of blockchain by the solution or the different solution providers may be a part of their solution, but the regulation itself never makes reference, to my knowledge, of blockchain. So I would have to say that would be a solution provider level question. I can't speak to their implementation.
Okay, another question we received is, why didn't we go for a simple symbol identifier followed by the FNC1?
If you're referring to the .code followed by the FNC1, the symbologist, Andy Longacre, who created .code, he essentially felt, I believe, and maybe George can speak to this later, but my understanding is Andy felt like GS1 would be a primary user of the symbology one day. And for that reason, he made it more efficient to carry GS1 data by one character, I guess, by saying that the rule for .code is not seeing the presence of function 1. Now, in fact, the rules for symbology identifiers for GS1 symbols are different depending on the barcode. That's already true, and that was true before .code. If you look at, for instance, QR code, there is a mode operator. It's not an explicit function 1, but it implies a function 1 in the start position. So there are very different ways of that, and we see that the solution provider community, sometimes within their implementations, of course, they may transmit a functional equivalent to the symbology identifier. But what is really critical is that all of the solution providers and all of the people who are specifying identifiers, whether it's GS1 as an ISO issuing agency, ISO IEC issuing agency, or any of the rest, that we all adhere to the same rules. Because if we don't, we can't swim straight in our own lane. And then we're going to start having swimmers colliding with each other as we're trying to go from one end of the pool to the other. Those rules, and AIM is the registrar of the issuing agency, and the rules in ISO IEC 15459, 15424, and the related sections in the symbology specifications allow the transmission of decoded data to work across all issuing agencies together in one application. And this application, Fighting Illicit Trade in Europe, is probably one of the most heightened examples of why we need those rules, because we have multiple ISO IEC issuing agencies, at least 4 that I know of, including GS1, who are involved. And because we're all following the same rules, and the commission and the secondary repository are making those rules very clear to everyone, all of our identifiers can coexist in the same application space without collision. So that's really critical. In fact, we could do, again, another, and we did that, if George will remember and others. GS1 had a session on exactly how to build the encode and build the decode for this application. Again, we can provide that link to AIM should anyone have an interest in following that for more information.
Okay, great.
Mike, it's George.
Yes.
May I amplify just a bit on this?
Sure.
So I think Scott did a good job of teasing out the fact that these were really 2 questions. But to focus on the symbology identifier and the complexity, quote unquote, of a 3-character identifier. The TSC developed that structure decades ago, and we had to be mindful that we had to introduce a prefix that would never, air quotes again, never be 3 characters of data that would appear in any obvious closed loop system. And so it is purposely odd, right bracket, alpha, digit, because no business message that would reasonably be used would start that way. It's also important to note that that data does not come out of the symbol. The symbology identifier is not encoded in any barcode. Rather, a scanner has a setting, and that setting being set on is required for GS1 implementations. Scott will attest that the general specifications have always been forthright about that. And so the scanner has the logic to identify the symbology type. The scanner has the logic to see what the initial data characters are, or the symbol characters. And the scanner then makes a determination as to which symbology identifier to append and transmit as a prefix. So in a most obvious example, any EAN UPC symbol is by definition a GS1 application. So those symbologies invoke back bracket E0. Code 128 with function 1 in the first position is therefore by definition a GS1 embodiment. And so that invokes back bracket or right bracket capital C 1. DotCode is an exception in that, in order to absolutely minimize symbol size for GS1 applications, the inventor turned the rule around and said that DotCode without function 1 in the first position shall be a GS1 embodiment. And so if someone wants to use DotCode in a closed loop system outside of GS1, that symbol will be burdened by the additional 9 data positions of encoding function 1. So I think the most important question we can answer and clarify, because we hear it so often, is that, well, where is the symbology identifier encoded in the symbol? It's not. Well, how does it get to be? How does it get in the data string? The scanner sends it. How does the scanner know? The scanner can auto-discriminate between symbologies, parse the leading digits to determine, or the leading data characters or the symbology characters, function 1 being one of the most important ones, and then make a determination. So thank you for the opportunity to amplify that.
That was really good, George. And I think one of the follow-up questions that people have often is, well, what happens if we don't have a symbology identifier? So if you look at the ISO IEC 15459 rules that govern how issuing agencies like GS1 must operate, it says that each of our identifier data fields must have a qualifier in front of them. But it doesn't say that our qualifiers have to follow any particular type of character. So for instance, GS1 uses numeric values in our application identifiers, but other issuing agencies that use the data identifier approach for data qualifiers, some of those begin with a numeric value as well. And so if you go straight from a symbology or without a symbology identifier into the qualifiers, it's not the qualifier which tells you whether it's a GS1 identifier that's coming. You have to have something first to say what you're about to see is a GS1 barcode, and or what you're about to see is not a GS1 barcode. So again, we could go for an hour on this and probably should stop given the focus today, but we do have a lot more information on that, and I'd be happy to share that with you, Michael.
Yeah, no worries. Just a few more questions before we move to Terry and George's portion of the webinar. We had a question, how do you avoid duplication of serial numbers?
Well, in the case of the third-party extension of serial numbers, GS1 is involved with 2 countries, with Spain and with Portugal. And our development, we've worked internally to produce an algorithm for years. We've worked on that algorithm. It's been deployed and has already produced I honestly can't even tell you probably hundreds of millions of unit packs. But the algorithm includes randomization of and different factors that guarantee that there will be never a collision between 2 serial numbers for a given G10. So there may be 2 serial numbers. It is possible, theoretically, for 2 serial numbers to be the same for 2 different G10s, but the GS1 serialized approach always requires the G10 as the key for the product identifier. This allows us to have a smaller serial number field and utilize that functionality. But the algorithm itself protects against that.
Okay, thank you. And how can you encode an AI235 in RAIN EPC RFID tags?
Okay, so as we went through this process, we updated all of the associated EPCIS standards. So for instance, the messages related or the events related to dispatch or receiving, shipping. And because of that, in order for the EPCIS implementation to work, we have a different syntax, which is called a URN. So that is the syntax that EPC uses, and that's codified in a standard called EPC Tag Data Standard. So as we introduce a new identifier data field, like this one or others, If we expect them to be required within the EPCIS implementation or within the RFID implementation, we codify how those would look in a URN. So again, at our website for illicit trade, there's a list of all of the impacted standards, and that would include our master data standards, our EPCIS standards, our EPC tag data standards, our EDI messages for order, invoice, and payment, as well as the general specifications for DotCode and the application standard for this.
Okay, and one last question I have before we move on. Does the flat file have to reside on the scanning device, or can it reside on the computer that the scanner connects to?
The way that it is described is it's simply saying offline. So if the scanning device were tethered to a computer, and that computer was offline, it would meet the regulatory requirement in my mind, because they don't specify the design of the offline device. They just simply say the device must accomplish this outcome in offline mode. So I don't think that they would go further than that to say, is it a tablet, or is it a a handheld, or is it a tethered device? Or I don't think they've gone that far in the regulation, but I can check. If I'm wrong, I'll come back to you, but I'm pretty sure that's correct.
Scott, George again. I think we understand generally, don't we, that while we may have been saying scanner, we're talking about a portable data terminal, typically, that might be a traditional handheld industrial terminal, but it might be a tablet. It might be an iPhone or an Android with sufficient memory to take a download. And that the people performing these audits are in fact, this is not store clerks or sellers doing this. These are customs auditors or others who have what will undoubtedly be specialized tools. Even if it's an off-the-shelf phone, it's going to have proprietary software, links to the cloud to receive these data downloads hourly, daily, weekly. Would you say that's a valid description of the model?
Absolutely. Absolutely correct. These are, you can imagine where a customs official would be operating. That's the environment in which the device would have to support. So you're typically going to see some type of portable device, and probably of some industrial capability. With the capability you also mentioned of taking regular or receiving regular updates. Obviously, those updates are online. So they have to be able to connect in order to provide updated algorithm versions, updated flat file data. So for instance, if a manufacturer were to add a new production facility with 10 new machines, before they produce anything moving through that factory, all of that data would need to be registered in the repository, impact the flat files, so that when the decode algorithm works, it can find those 10 new machines in that new factory. So that device would have to get an update.
And by the same token, that device will regularly report the good, the bad, and the ugly, the transaction data, the audit scans that are taken, and the conforming or the non-conforming results will ultimately get back to the National Registry, the tax authority, whomever.
Well, It's true, except for the role. As far as the data that is used in order to survey or use employ surveillance across the supply chain, that comes from the supply chain stakeholders like the distributors, the wholesalers, the manufacturers and importers. So they are capturing that data using, for instance, event data. And so the customs official role in utilizing the device for offline scanning is essentially, if they suspect there is something wrong, it's a tool that they can use in order to try and determine what has gone wrong. There, they then can interact with the member state authorities and the regulatory database. But the access to that data and the input from that data, input of that data, the input comes from the stakeholders and the access is to the member states and the commission. Even the secondary repository provider themselves don't have access to the surveillance data. They provide it, but they don't have access to it.
Good clarification, thank you.
Mm-hmm.
Okay, well, Scott, thank you so much for your time and information today.
Thank you, and thank you to AIM for everything you do for all of us. So thank you very much.
Now I would like to turn it over to Terry Burton and George Wright as they discuss in detail the DotCode 4.0 revision. Welcome, gentlemen.
Thank you, Mike. It's nice to be here.
Thank you, Mike. Yep, likewise.
So, Terry, I'll kick it off. Please take a moment to read this red box warning. The composite representation that you see here of the cover page of the DotCode AIM International Symbology specification is reproduced to emphasize the fact that this DotCode revision 4.0 is not just some minor revision. There are significant changes to the symbol generation process, that is, to the encoding process. And the specification starts out by telling you in bold print, pay attention. Further details are provided in the revision notice, which is a few pages down in the spec. Before we move on to the meat of this part of our presentation, I should tell you that it's my intention to review the bullets on the slides and then to provide some further detail. The bullets are the key points, and by and large, they weren't being read aloud. If all you had was the slide presentation and no further commentary, you would still know what is important in DotCode revision 4.0. But luckily, you have Terry and me here too to offer further insights. So enough said about the style of presentation, at least mine. Terry may likely take a little bit different tack. So with that having been said, I'll just point out that this AIM webinar is not intended to be an in-depth tutorial on changes to the DotCode spec, but rather a comprehensive overview of what has changed in revision 4.0. As I said, the goal is to highlight the key points and to provide some further explanatory comments in the discussion. And at the end, like we've done with Scott's presentation, to answer questions submitted in writing via the chat box. Individual participants and organizers who need to dig in depth into this should go to the AIM website and buy the new DotCode 4.0 specification for complete details. Revision 3 versus revision 2. Yes, this is a presentation about revision 4, but it's important to make these observations. DotCode 3 was published with substantial formatting inconsistencies and was withdrawn. But the fundamental encoding and decoding methods in Rev 3 do not differ from revision 2. Therefore, implementations that follow revision 3 are essentially indistinguishable from revision 2. But both implementations suffer from the problems identified and fixed in 4.0. Why do I make the point about this? Because users following regulatory or internal standards referencing revision 3, such as the EU directive, and even the 2020 version of the GS1 general specifications. Those users using revision 3 are equally valid, those embodiments, to those employing revision 2. Well, at least, or no more disadvantaged. There are flaws, and so we strongly suggest that users who are not restricted to a particular revision of DotCode should, without a question, choose 4.0, and regulations and applications that may stipulate 3.0 or even a prior version should be reviewed and updated to reflect the current standard. The crux of this is to say that while the EU implementing regulation 2018/574 cites revision 3.0, overall system scanning performance in this application will be improved where DotCode symbols are generated in accordance with the new spec and not 3.0. What's changed? Technical errors and weaknesses, including a critical structural issue, were identified and fixed. The text of the standard, the normative descriptions, clarifications, and editorial corrections have been made. Significant updates to symbol print quality grading have been defined. And consequently, printers and encoding software must be updated. Readers, happily, need not be updated. And barcode print quality verifiers must be updated. The fact of the matter is that with the exception of, I shouldn't say with the exception, but the fact of the matter is that satisfactory solutions have been found to the structural issues, and these are included in the new revision. But unhappily, there was no choice but to violate the prime directive of barcode standards revision and impose a change on the encoding. We did not, however, violate the other prime directive, which is to change the reference decode algorithm. If you had to change one thing, better to put the onus on the encoding side than on the decoding side. Point to be taken is that the install base of DotCode readers is unaffected. So on that happy note, over to you, Terry.
Thank you, George. So despite there being a number of significant changes made in revision 4.0, those changes are actually made in a very specific part of the encoding process. So anyone in the audience who has any background in barcode encoding will note that the numbered points in this slide represent discrete steps in the barcode generation process. So we'll work through them. So step 1, the shape and orientation options. So in terms of DotCode, the full gamut of dot array sizes, orientation options, are still available and they've not been changed. However, for step 2, where we have to choose a particular size of DotCode for an application, the weaknesses that we have learned sort of recently in recent years about DotCode have meant that we now have augmented the set of user considerations to assist users in picking an optimal size DotCode symbol for their particular application. In step 3, 2D barcodes store messages as sets of code words, and nothing has changed in terms of turning the user message into a set of code words. So we mentioned before that DotCode has this unique setting, if you like, that ensures that GS1 barcodes or barcodes carrying GS1 data are optimally represented. So we, in fact, omit the FNC1 to indicate the GS1 data rather than include it. So there's no change in this. The encoding is just the same. Likewise, the Reed-Solomon algorithm, which is the error correction algorithm employed by DotCode, hasn't changed. So revision 4 and revision 3, revision 2, whatever message you give it, the error correction encoding will be the same. Steps 5 and 6 are where the code words representing the message are convoluted and then laid out in the matrix to produce a set of 4 candidate symbols. The idea being that if if one symbol generated by this process might not be optimal for some reason, then you have 4, and so hopefully one of those 4 will be much better. However, we learned that there were some issues, and that sometimes, even with these 4 candidate symbols, none of those 4 candidates were actually very acceptable, and they could also generate symbols that would not scan. So there is an entirely new process in DotCode revision 4, which is employed in some cases to generate new mask candidates, and from those new mask candidates, the best is chosen. So hence, that's why printers and encoders may need to be updated. In fact, will need to be updated with DotCode revision 4. And finally, just returning to the things that haven't changed. So there's been no change as far as decoding is concerned. So the reference decode algorithm is the same. There's no change required for scanners or decoders. And there's no change also in the transmission protocol. So the symbology identifier is identical to what we had in the previous revisions of DotCode. So all the changes are in the mask evaluation process, which is one specific area. However, this does have implications for some of those other processes in the encoding, which we'll look into. So before we look in any more depth about the changes that have been made, it's worth introducing a notion of robustness. What we discovered while we were looking at implementations of DotCode is that the encode algorithm for DotCode could actually create symbols which we might say were broken or lacked robustness. And it's helpful to introduce that concept. So scanners decode symbols by looking for the presence and the absence of ink at expected locations. And to identify those locations, it's necessary to extract the .code.array from an image. Whereas other 2D barcodes have things like finder patterns, alignment patterns, and timing patterns, which are like fixed properties of an image, DotCode has none of that. And in fact, it's very lean. All of the dots are lit on the basis of the data encoded in the message. So there's no overhead from creating those. That does mean that DotCode scanners must go to extra length to ensure that they can decode the symbol. Now, certain visual properties that can arise from ordinary message encoding can make a symbol much more difficult for scanners to decode. And so what we have in this next page is the set of the set of desirable and undesirable properties that you can find in a DotCode symbol, which will either help or hinder a symbol from being read. So the first thing is that if we have a large number of dots along all of the 4 edges, that actually helps to improve the scanning performance. Whereas if we have a number of interior rows or columns in the dot array which are lacking dots, then that's a hindrance. So if we take a look at these symbols at the bottom of the screen, we see that these are 4 different masks for the same data. So a user has come along, they have some data to encode in a DotCode, and DotCode firstly generates 4 symbol candidates. Now the idea is to pick the best one. But in the case of this, we find that all 4 of the masks have some flaws. So in the case of the symbol on the left, we see that there's an unprinted row, which is highlighted. And this becomes especially problematic for reasons that George will explain in a moment, when that unprinted row is a perimeter edge. So if we take a look at the symbols on the right-hand side, we can see that the one on the right-hand side has a missing left edge, and the one next to that has a missing top edge. And then additionally, we can see in the rightmost symbol that there's also a number of standalone dots. And these are also problematic as far as decoding a symbol is concerned. And then finally, if we have a look at the symbol second to the left, we see that there's a large void. So these are all things that can help or hinder and in the majority of the cases we mentioned here, hinder a symbol from being scanned successfully. Now, here's the large problem. In prior revisions of DotCode, it's precisely this problematic right-hand mask, the symbol the rightmost symbol there, with its multiple issues, the missing edge and the lone dots, that is actually chosen by the mask evaluation algorithm to be the symbol for DotCode for this data. And if you were to try to scan these symbols, you may well find that these rightmost two symbols have great difficulty being scanned by either a mobile scanner or a handheld scanner. So George will now introduce why this particular cases cause a significant problem.
Thank you, Terry. So the most egregious situation, one we call more than problematic, is the missing perimeter edge. It's pathological. The last bullet on the previous slide quoted from the spec and noted that the goal of avoiding unprinted exterior or perimeter rows or columns of the dot array was an important one. This goes to the heart of the structural problem with the original embodiment of DotCode. The DotCode encoder algorithm prior to version 4 can generate symbols, as Terry pointed out very clearly, with missing perimeter edges, but with alarming regularity, especially in smaller matrix sizes and certain array dimensions. Terry will go into that again a little bit down the road. The bottom line is that when there is a missing perimeter edge, the DotCode symbol is no longer an odd by even sized matrix. That's a fundamental requirement of a DotCode symbol. Unlike data matrix, it's not a perfect square. It must be odd by even. And when it's not, the reference decode algorithm fails. It's an F grade, period, end of story. With this slide, we begin to get a hint into the weakness of DotCode encoding, into the weeds and the weaknesses of DotCode encoding. But we promise not to get too deep, but it has to be said that DotCode is different from other 2D symbologies. As Terry said, there's no fixed finder pattern. We have to rely on the integrity of the data dots themselves. In data matrix, for example, like DotCode, the error correction level is fixed, but with data matrix, if one follows the optimal encoding algorithm, which minimizes symbol size, one gets a certain pattern of black and white cells, and that's the pattern one prints. As Terry pointed out, with DotCode, following the same sort of optimization algorithm, one gets a prospective bit stream, that is, a pattern of black and white dots, which might or might not exhibit graphical robustness. Therefore, the DotCode encoder software, whether it's embedded in a printer or as a standalone application, must produce, by definition, 4 candidate symbol patterns for evaluation. This is done in logical memory in real time, and even on a high-speed line of tobacco packaging cigarette packs to the tune of 1,000 a minute, that encoder must produce those 4 candidate symbols, grade them, evaluate them, score them, and then pick the best one. In this example, among what are actually 4 fairly weak graphical patterns, Terry pointed that out, the highest scoring pattern in the upper left actually has a missing bottom perimeter edge. Those 2 circles of green that are not filled in are 2 of the 6 DotCode corner dots. They're the only 2 data dot positions that are potentially that are in the bottom row, and they happen to not be printed. Or as Terry coined, lit. If you hear us talk about lighting the corner dots, consider that we're saying printing the corner dots. And I'll just make an aside and say that DotCode supports white on black as well as black on white. So understand that an image could be reversed if the application called for it. But so here we have 4 candidate symbols, all of which are fairly weak. And it was discovered that this was happening in an in-depth inquiry that AIM undertook, and with the help of some newly arrived contributors, namely Terry Burton and Robin Stewart, both of the UK, a massive algorithmic analysis was conducted of tens of millions of symbol patterns. And as a result, we discovered exactly under what circumstances the missing perimeter edge phenomenon can occur. I'll let Terry tell you all about that.
Okay, so I'll just give a bit of an intuition here. If anybody's interested in more depth, then do indicate that in the chat, and there's more analysis that we can throw at this. So effectively, we want to know under what circumstances a missing edge can arise, and then what we might do about it. So firstly, DotCode is what's called a 5 of 9 code. And that essentially means that every code word arising from information in the user's message is represented graphically as a group of 9 dots. 5 of those 9 are printed and 4 are not. So for even height symbols, if we take a look at this figure on the bottom left here, this sort of shows the layout of those dots. So the data is laid out down the columns and then moving along from left to right. So the dots there, which are indicated with the A and the B, initially they indicate the mask. And then from C, D, E, F onwards, 9 dots, we have the first code word, followed by the second code word and the third. And then the user code words followed by error correction code words. So lots of groups of 9 dots filling the symbol down the columns and along from left to right. And the important point is that there's 6 corner dots there which are highlighted. And it's those corner dots which are reserved, and they're skipped over during the normal layout of the data, and then they're visited last. So these corner dots contain either the last code word, or in the case that the data doesn't fill the symbol, as can happen, they contain pad dots. So they are artificially printed just to make up for the data that isn't there. It's better to print a dot than to have no dot. And this is kind of a crucial point. So noting that those those last 6 dots can either be representing the final code word, an error correction code word, or a pad dot, we can start to draw some conclusions. So the table on the right-hand side is quite interesting. So the number of pad dots in any data matrix, in any DotCode symbol, is a simple function of the DotCode size. So if we have a look at this table, there's 2 points that we can pull out. Firstly, we can see that there is a cross there through the middle of the symbol, and along the bottom and along the right of green cells containing a 7. Now, those are precisely the symbol sizes where there are 7 pad dots. Now, of course, if there's 7 pad dots in the symbol, that means that all of those 6 final corner dots are printed because they're pad dots, and by definition, we print them. Now, an interesting feature is that if we light the dots 6, 5, and 4, then we can guarantee that a symbol which has 6, 5, and 4 printed will not have any missing edge. Why is that? Well, if you imagine printing the dot 6, well, you've effectively protected the top row and the left row. And if you print the symbol 5, you've protected the top row and the right row. And then finally, if you printed the dot labeled 4, you've protected the bottom row. So just by printing 4, 5, and 6, you can guarantee that such symbols will not have a missing edge. And so precisely in this table, the cells which are black text on a white background are those cells where there's a guarantee that those 3 final corner dots are printed. And then finally, the cells in red are those where where there's no guarantee that those cells 6, 5, and 4 are printed. And so it's precisely those cells in red that can have the pathological case of a missing edge. Now, if you haven't followed that logic, no matter, this table is very good because it offers a generalization. So what this table allows us to do is to maximize the graphical robustness. So if you have an application of DotCode that uses variable length data, or where the user data, when it's encoded into code words, could have a variable length number of code words, then providing you can fix one of the axes, that the size of one of the axes of the DotCode symbol to a multiple of 9, then all symbols resulting from that will have a robust immunity from the missing edge problem. So that's exactly this for existing applications. If you can fix the size of a single edge to a multiple of 9 dots, then you cannot possibly have any symbols which have a missing edge, and it does so robustly. Secondly, if you have an application where you can, by the nature of the application, choose a carefully curated set of sizes, specifically those with the black numerals on the white boxes, then you can also avoid the missing edge problem. But the level of robustness may not be as good as fixing it to a multiple of 9. So what can users and implementers of DotCode conclude from this analysis? Well, even if your regulatory and internal standards require that you use some prior version of DotCode, but your application has the freedom of choice over the set of DotCode symbol sizes that you generate, then revision 4 contains guidance that will help to mitigate the missing edge problem, even using your existing encoder. So you should nevertheless review the DotCode revision 4.0 specification, even if you're stuck with implementing an earlier version, because the DotCode revision 4 specification provides specific guidance to help you pick symbol sizes that will make sure that your application is robust to this missing edge problem. Okay, George, over to you.
Thanks, Terry. So as I said earlier, the prime directive of barcode symbology revision is to avoid it if you can, but never to break the reference decode algorithm and compromise or invalidate the install base of readers. And we've succeeded. We did not do that. We applied a fix that does change the encoder, but allows existing readers to continue to function without any modification. As Terry pointed out, we have scoring algorithms for the candidate masks. Those scoring algorithms are weighed against a threshold, which is height by width divided by 2. And if those 4 candidate masks don't meet that threshold, we print or light the 6 corner dots, rescore, and choose the best modified symbol. A graphical representation of that is right in front of you. We've seen the top row of mask candidates in this table before when we defined our notion of graphical robustness, which they all lack. This is reflected in the original 2.0 and 3.0 scoring, highlighted in yellow, which shows that each of the mask scores is in fact negative. Moreover, the best scoring mask under the original scoring, mask 0, the upper left mask, has a missing left perimeter edge, but it's the highest scoring symbol and would be selected. If you look at the right-hand symbol, mask 3, that's the second highest scoring symbol, and it's missing a perimeter edge. So clearly we have a problem. Under revision 4.0 scoring, both of these, what we call pathological symbols, are now scored harshly. They're penalized with a score of negative 99,999, which effectively excludes them as candidates. No other symbol will have a grade so low. The scoring of the remaining candidates is unchanged. Now, since no mask candidate of the 4 across the top row is good enough, none of them meet the threshold of the number of rows by the number of columns divided by 2. They're all negative numbers. They're nowhere close. We've satisfied the condition, the need for triggering this new process of lighting or printing the 6 corner dots. Some of them may already be printed, but the rule is to arbitrarily assure that all 6 corner dots are printed and then to rescore the masks. So we really have 8 masks, the original 4, and then what we call the prime masks, which are those same dot patterns with the corner dots lit. The revised or prime masks are rescored, and they're unavoidably more graphically robust. In fact, in this instance, they all satisfy the threshold test, and we choose mask 0 prime in the lower left-hand corner because it has the highest score. Again, note that mask 0 prime is the same dot pattern as the one above it, but the 6 corner dots are lit or are printed. And it's this unique approach that allowed us to eliminate a missing perimeter edge with a very small penalty in error correction and not have to, in fact, change any reference decode algorithm. I'm going to try to pick it up here because we want to save time for questions and end on time. What are the intended consequences? Well, for the symbols that previously had a missing edge, usually one of the other 3 masks is satisfactory. Only if all 4 of the masks fail the threshold test will we then rescore with the 6 corner dots printed. And existing readers will decode these modified symbols without the need for reprogramming. The vast majority of symbols, without a missing edge, but the vast majority of symbols that are printed, approximately 99%, continue to be generated even under DotCode Rev 4.0, just as they were in the previous revision of DotCode. But what about that intentionally introduced error that we introduce into the last code word by lighting the corner dots? What effect does that have? Well, in technical terms, it's treated as an erasure, and it's fixed by the Reed-Solomon error correction. One erasure is the least possible amount of damage that can be inflicted on a 2D barcode symbol, and the easiest and quickest for the scanner to correct using the Reed-Solomon error correction. Reed-Solomon is inherent in all modern 2D symbols. It's a feature of DotCode, QR code, data matrix, Aztec code, and many others.
So the ultimate extension to George's question about what happens if you modify that final code word is, well, why can't we just start arbitrarily lighting any dots we choose? Well, of course, if we do that, we change the meaning of the symbol. Now, the thing that protects us from changing the meaning of the symbol is the fact that DotCode has built-in error correction. So to an extent, we can change some of the dots, and the error correction can compensate for that and not change the meaning of the symbol. The question becomes, well, to what extent can that happen? And DotCode has, Reed-Solomon in DotCode has an interesting property that can be thought of as a budget for the error correction. So if you think of it as a budget, and let's say that we have a number of credits, so which we call unused error correction. So we start out with a number of credits which is equal to the number of error correction code words in the symbol. And for DotCode, 33% approximately of the code words in a DotCode symbol are used for error correction purposes. So we start off with 33% of our total number of code words as being our budget. Now, if we introduce an error in a position and the reader is unable to detect where that error is, but knows that it's there, then we consume 2 of our credits. But if we know the position of the error, then we just consume a single credit. Now, because DotCode is a 5 of 9 code, if we light some dots in the final code word, then we've created a detectable excess of dots in the symbol in that final code word. So we have an error, but we know where it is. That's what we call an erasure, and that means that we impact the error correction by the smallest possible amount. So if we ask what's the impact of introducing an error in that final code word, well, it's the smallest possible amount that we could make. Now, it may well be that we can correct the data unambiguously, but we need to make sure that there's no additional costs to creating an error, to impacting and creating a change in the code word. The question would be, therefore, why not always light the 6 corner dots? Now, what we're looking at here, with the kind permission of Dr. Kevin Barissa with the AIDC lab at Memphis, is some test apparatus that's been used for doing some empirical testing of DotCode's robustness, precisely in the event that we inflict damage upon code words. So if effectively each of those tablets on the apparatus contains a random DotCode symbol with a random DotCode message, and the thing that we're seeing there at the top is a scanner, which is at a fixed location above those tablets. Now, of course, other brands of scanner are available, but effectively what Kevin did was to do multiple runs of scanning these symbols with differing amounts of code word damage, and then to analyze the effect of the on scan times of introducing increasing amounts of code word damage. Now, Kevin has made this research, the paper publishing this research, available in an open access repository that you can access for free and without any requirement to register. So if any of this is interesting to you, then I suggest that you follow the links there, and you'll eventually find that paper and have a good review of all of the testing methods and the results that come from it. But for us now, we're just going to look at 1 or 2 of the results from that paper, which are relevant to the case of lighting the 6 corner dots. So take it away, please, George.
Thank you, Terry. The simple fact is that any damage that invokes error correction is costly. It increases decode time and scanner variability. This is a table of the performance of one particular scanner documenting 7 different runs with various amounts of and kinds of damage, as shown on the previous slide. And again, the significant conclusion is that damage equals more latency and more variability. This might be self-evident, but we have the empirical data to prove it, and that's one of the reasons we ignored or discarded the notion of arbitrarily lighting all 6 corner dots. There was too big a penalty to pay, and it's an unnecessary burden. This is where I'll turn it over to Terry to talk to you about empty rows and columns, and we'll try to wrap up quickly and answer some questions. We may run over a bit, but we'll try to hurry through these.
Yeah, so very briefly, what we detected was that in addition to the missing perimeter edges, the original code, which was included in the specification for doing mask evaluation, could also, under certain circumstances, not see missing internal rows and columns as well. A missing internal row or column can have the effect of almost chopping a single symbol into multiple symbols. So that can have a significant impact on the decodability. There was also a programming mistake, which could mean that if a mask got a significantly bad score, then there could be a numeric underflow, which effectively promoted that mask to having the highest score of the set. So in fact, the worst possible mask could also be chosen. So obviously the code, which was provided in the form of C code, was fixed, but additionally we created a normative textual description of the intended mask scoring process. So a action on anybody who is an implementer of this is to ensure that they are aligning with the intended process rather than just some example C code, in case that that code contains yet to be discovered bugs. So this issue was resolved. Okay, so in terms of new things, DotCode isn't just about fixing things. There is actually some new content which was introduced. One of those things was that there is a new coordinate system. Now, the aim of the new coordinate system was to solve the problem where we'd find that verifier manufacturers would report that there was an error at a particular code word location or a particular location in the dot array, but there was no universally accepted standard for how to identify the location that was being reported. So the new coordinate system provides a reference algorithm for finding specific dot locations. And we would ask that verifiers consider adopting the reference coordinate system for DotCode, not only for consistency, but also because the method that's been chosen is actually quite easy to explain to the layperson in terms of graphical features as to how they might find the specific dot that's in question, that's being reported.
We'll leave it to the individual participants to get a copy of the spec from the AIM store and uncover as necessary what the new print quality parameters are, how they're defined, and the fact that they anticipate the forthcoming changes to ISO IEC 15 for what's called continuous grading to 1/10 of a point. And also note that we do have ungraded parameters called the mask array score and the mask array threshold that verifier manufacturers shall report so that users will have a notion as to how graphically robust their symbol under test is. Other errata and inconsistencies don't bear being reviewed here, particularly with the lack of time. The revision notice points to them all. And again, if you have the new spec in hand with accompanying source code, so the C source code is part of the purchase on the AIM store if you need it for development. To recap, 3 was withdrawn formally, but is still cited by the European regulation and GS1, and the implementations, while valid, are handicapped by the deficiencies we uncovered. We would encourage those who have a choice to adopt version 4.0, and for regulators around the world who can undertake to review their requirements to move towards recognizing the upgraded version 4.0. And finally, just to repeat, printers and coding software must be updated, verifiers must be updated, but happily, readers need not be updated. So with that, I'll say thank you on behalf of Terry and myself, and we have just a few minutes for questions. And Mike, if you can sort through them, and we'll tick them off as quick as we can. And for anyone who can stay beyond the allotted time, we don't mind running over on our part.
Yeah, thank you, George and Terry, for your information today. We still do have some time for you to send some questions over through our chat option, but I will go through the questions that we do have right now. One is just in general, is there a plan to move DotCode through ISO IEC? Yes,
absolutely. That is the plan.
Okay. Another question that we do have is there additional to support for developers using DotCode to implement it?
Yeah, I can pick this one. So as well as the printed specification document, there is also a reference encode and DotCode kit available from the AIM store. So that contains code which has been refreshed as part of the activities for revising the specification. And implementers should feel free to go ahead and look at that and implement. But as a general principle, as we would say before, reference code is great, but a lot of the work that has gone into the revision of the specification is to create new normative textual descriptions of intended processes. So the idea being there that if there is some error in code, and all significantly complex code contains some bugs, then you should align with the intent of the specification. And in doing so, if you find any issues, then report them back. But all the known issues with the previous, that apply to the previous encoder software with respect to the weaknesses of DotCode have been addressed.
Terry, I believe I'm correct in saying that the C source code that's provided is for the encoder. I don't believe there's a reference DotCode source code.
Okay, I'll take your point on that. Yep.
Next
Okay,
question.
great. Yeah, George, another question that we have is, in regards to DotCode, do you see it being used in the cannabis industry?
That's a good question. Hard to say. One might envision it, but right now bear in mind that in the GS1 arena, DotCode is only approved for use in this one application, and in Europe at that. I think DotCode, as much as we think as symbologists that it has technical merit beyond what other symbologies offer for high-speed printing by continuous inkjet or laser, whether it's on small packages or even moving down a conveyor line. As much as we think DotCode has a place in the universe of necessary symbologies, the market is going to dictate this. I think we're going to have to see how DotCode fares in the European tobacco industry, see whether it continues to work alongside the other symbologies that various national authorities allow, to see whether the GS1 embodiment works better than other embodiments. But there's no doubt in my mind that the traceability of controlled products is going to be a growth market. And tobacco beyond Europe, and if we can do it in tobacco and the solution providers build the systems they're building for this application, those systems will very readily translate to the track and trace and the counterfeit detection of wine and spirits. And whether that's in the European market segment first or elsewhere, I don't think we can say. But certainly at this point, we feel like DotCode is a robust and reliable symbology, and that it will find new homes in places that haven't really been discussed yet.
Michael, do you mind if I also provide some background? I think when we talk about a product like cannabis or any wine and spirits or any particular product, I think we have to think about where we're talking about using barcode technology. So, for instance, in the EU regulation, there is no requirement for point of sale scanning. However, there might be in the future a requirement for inline serialization at extremely high speeds, and that serialization to be used at point of sale. In that event, what I believe need to do, and I've spoken to George and Dan and others about the TSC at AIM and the BCID GS1, looking at the robustness of omnidirectional scanning, and we need to think about in the future kind of a reference build for scanners that are going to support GS1 applications. And I think that merits probably another webinar to think about, where are we today, where we might see ourselves in the future. But DotCode, at least from GS1's perspective, has met the hurdles for our adoption of it for one application. Were we to look at an application impacting point of sale, then I think we would definitely look for a lot of data on the omnidirectional performance of DotCode.
Okay, great. Another question, George, maybe you can answer this. Was DotCode inspired by Code 128?
Absolutely. And Andy Longacre said so, I think, as much in the standard. It was meant to replicate Code 128 in its capacity, its functionality, its double density numeric feature, its multi-code set. So very much meant to be a 2D, omnidirectionally scannable, white on black, black on white symbology derived from Code 128.
Okay, great. That's all the questions we have for now. Want to thank you, George, Terry, and Scott, again for your time and insights today. Really appreciate it.
Thank you for the opportunity, Mike. We appreciate it.
Thank you, Mike. Thank you,
and
Mike.
if you would like to purchase the DotCode symbology, specification, and encoder software, it is available now in the AIM store. If you would like additional information on DotCode, the work group it originated from, or AIM and our initiatives, please contact us at info@aimglobal.org or call us at 724-742-4470. Thank you to our audience for their active participation today. And once again, thanks everyone and have a great day.